Let's talk about diagonalization. So I want to begin this lecture with a sort of motivational example that is easy to grasp, but yet still important. In this example, let's start by looking at this simple 2 by 2 matrix. And I say this matrix is simple because it's a diagonal matrix. The diagonal entries are the numbers 1 and 2, and the off-diagonal entries are both equal to 0. So in this example, all we want to do is we want to take this matrix and raise it to the 100th power. Now, if we think about what this means is that we want to multiply this matrix by itself 100 times. And because this matrix is diagonal, this is not a very difficult problem. All we need to do is take the two numbers on the diagonal, 1 and 2, and exponentiate each one to the power of 100, and we still get zeros on the off diagonals here. So this problem is actually fairly simple. All we need to do to raise this matrix to the power of 100 is take each of the diagonal entries and raise them individually to the powers of 100. So the punchline here is that this problem is easy to solve, and the reason this problem is easy to solve is because the matrix in question is a diagonal matrix. Let's now turn to a more complicated version of this example. So now instead of taking our simple diagonal 2 by 2 matrix and raising it to the power of 100, let's work with a more complicated 2 by 2 matrix. Here our matrix has columns 5, 6, and -2, -2. So the question is, how are we going to take this matrix and raise it to the power of 100? Because this is not a diagonal matrix, we cannot simply exponentiate each one of the entries in this matrix to the power of 100, because that's not how matrix multiplication works. So here's a bad approach to the problem. So this isn't an unsolvable problem, but the problem really is finding an efficient way to solve the problem here. So one thing we can do is we can try to do lots of matrix multiplication. So the first thing maybe we can do is we can calculate a squared by taking a and multiplying by itself. And when we do the arithmetic here, we end up with the matrix whose columns are 13, 18, -6, -8. Keep in mind that it's evident from this very first step that even to square this original matrix, we're not simply squaring the individual entries inside of the matrix. So we took a, we multiplied by itself, and we found a squared. Then maybe we can calculate a to the 4th by taking our result from finding a squared and multiplying it by itself. So now a squared times a squared is equal to a to the 4th. So we're a little bit closer to a to the 100. Then maybe we can calculate a to the 8th by multiplying a to the 4th by a to the 4th. Then we can find a to the 16th by multiplying a to the 8th by a to the 8th. And you can imagine running through this process over and over and over again until eventually we reach a to the 100. And the problem is, this is a fairly bad idea because this requires us to do a lot of work on our own. And at the end of the day, it shouldn't be terribly difficult to simply take an algebraic object and raise it to the 100th power. So even though this idea of successively multiplying our matrix by itself over and over and over again will eventually get us a result, I still think this is a pretty bad idea because it's not very efficient. So if I'm going to tell you something is a bad idea, it's probably my responsibility to tell you what is an alternative to the bad idea. So what would be a good idea here? Well, let's say that somebody is nice enough to take our matrix A and express it as a product like this. Here, someone took the trouble to find A and then factor it as a matrix P times a diagonal matrix D times the inverse of our matrix P. So what we're going to find throughout this lecture is that factorizations of matrices that look like this end up making the matrix easier to work with. One thing I want to point out is the matrix D that was obtained in this factorization is exactly the D that we started with in the very first example. And to take D and raise it to the power of 100, all we need to do is raise each of the diagonal entries to the power of 100. So the problem we're working on is hard for the matrix A, but it's easy for the matrix D. So now, what would the nth power of A look like? Again, someone bothered to find this factorization. Maybe we can use this factorization to figure out the nth power of A. Well, the nth power of A is obtained by multiplying A by itself 100 different times. Or n different times if we're trying to calculate A to the n. And if we stare closely at these products, we realize that something nice happens. So in the first factor here, we have P times D times P inverse, because that's what A is equal to. And then we have another copy of P times D times P inverse. And what we find in the middle here is that we're multiplying P inverse by P, which is the identity matrix. So P inverse cancels with P here, and we're left with D multiplied by D. The idea is that if we keep canceling these inner P inverses with P's, what we end up doing is we end up multiplying by D, or multiplying D by itself n times, although we're still left with the original factor of P on the left and the original factor of P inverse on the right. So if someone hands us A equals P times D times P inverse, we immediately know that A to the power of n is really just P times D to the power of n times P inverse. And this unlocks the key to our problem of figuring out A to the power of 100. To calculate A to the power of 100, all we need to do is take our P that someone gave us, multiply by D to the 100, which is easy to calculate because D is a diagonal matrix, and then we multiply by P inverse on the right. When I did the arithmetic here, I ended up with this matrix on the left. The columns here are 4 times 2 to the 100, 6 times 2 to the 100, and then the column on the right is 2 minus 2 times 2 to the 100, and 4 minus 3 times 2 to the 100. So we've now solved our problem in one step, rather than have to multiply our matrix by itself over and over and over again. So a natural question to ask is, well, where did that factorization come from? Somebody is just handing it to us, but where did they find it in the first place? So what's going on with this expression, A equals P times D times P inverse? Well, let's take a closer look at the data inside of these matrices from the previous example. So in particular, what I want to do is I want to take A and I want to multiply by each column of P. So the matrix A we've been working with has columns 5, 6, and -2, -2. And the first column of P was the vector 1, 2. Well, when we take A and multiply by that column vector, we end up with 1 multiplied by 1, 2. When we take our matrix A and multiply by the second column of P, which was the vector -2, -3, we end up producing the vector 2 multiplied by -2, -3. So it looks like what's happening here is that the first column of P is an eigenvector of A, whose corresponding eigenvalue is 1. And it looks like the second column of P is an eigenvector of A, whose corresponding eigenvalue is lambda equals 2. So if we put all this data together, we end up with a nice matrix equation. If we take the columns of P and put them back into the matrix P, we end up with an equation that says A times P is the same thing as P multiplied by D. Because when we multiply A by each of the columns of P individually, all we end up doing is scaling the columns of P by the numbers 1 and 2. So one thing to pay attention to here is that in this equation, the P has columns that are eigenvectors of A, and D has diagonal entries equal to the corresponding eigenvalues of A. And if we look closely at this equation, A times P equals P times D, so A times P equals P times D, we realize that we can multiply it on the right by P inverse to obtain our desired factorization. A equals P times D times P inverse. So this sums up our motivational example. The original problem was to calculate a power of A. And what we found was that working from scratch was incredibly inefficient. Instead, we can search for this nice factorization, A equals P times D times P inverse. And once we have this factorization, we can quickly solve our problem of exponentiating A. Well, where did that factorization come from? What our calculations here are telling us is that we should find eigenvectors of A and put them into the columns of our matrix P, and then find the corresponding eigenvalues and put them into the diagonal of a diagonal matrix D. This is the core idea behind the concept of diagonalization.